Hello, decision scientist. Let's start the seventh topic on decision science for operations management. That is the second session on distribution and network models. In the last session, our focus was on supply chain models that we did that generator transportation problem together. Supply chain models in our class covers two categories. One of them is transportation problems that we did last session, and the other one that is very similar to the first one is transshipment problems that we are going to do today, and we are going to do it fast because it's very similar to the one we did last session that was transportation problem. Okay, transshipment problem is what you are seeing in front of you now. On the left, you see Denver and Atlanta. They are plants over there. They are origin nodes, very similar to the case we discussed together last session. On the right here, as you see the arrow, they are retail outlets, destination nodes, or distributor if we want to make it more similar to the one we discussed together last session. So here we have demands, very similar to the previous one. But the points, the parts that is different today, if you check the slide in front of you, you may notice that they are these transshipment nodes. Transshipment nodes are in fact connecting nodes. They are not origin or destination. They are not part of supply or demand. They just connect the points. For example, if I want to give you a simple example, just imagine you are traveling with airplane from, for example, Birmingham to, let's say, Boston. And okay, origin is Birmingham, Alabama, and the destination is Boston, Massachusetts. But we are gonna have a transit, a layover. That layover is not the destination, but is something necessary to be able to go from the origin to the destination. It is called transshipment nodes. And of course, in more real networks, we have many of them. And the good news is that when you know how to deal with transportation problems, it's very similar to handle transshipment problems. And we are going to do that together. As you can see, for transshipment nodes, there is no constraint in terms of demand or supply. Anything that comes into, for example, Kansas City can get out to any of the destination. Take your time and check this graph you see in front of you before we go further. Since transshipment problems are of the same type as transportation problem, and they both are in the category of supply chain models, as you saw previously here, supply chain models, decision variables, constraints objective function are very similar. Some of these items that I just mentioned are 100% similar. Some of the other are to some extent similar. Let's start with the decision variables. With the decision variables, when you look at this, what are the decision variables? Since you know the decision variables with transportation models are double subscripted and they cover the origin and destination indices, here you need to extend your knowledge in this way that, for example, if I say x 1 3, what does it mean? It means the number of items from Denver to Kansas City. No problem, Kansas City is not a destination node. But if you consider only this part, of course, it is the origin and it is the destination. So x13 would be the number of items shipped from Denver to Kansas City. What would you say if I write x2 4? The reason that I tackle the answer this much quickly because they are very similar to the previous one. x2 4, the number of items shipped from Atlanta to Louisville. What about x4 6, the number of items shipped from Louisville to Miami? And like that, we have decision variables. One of the points you need to pay attention is that to be able to better track decision variables, here we have continuous type of numbering: 1, 2, 3, 4, 5, 6, 7, 8. So in that way, you with just 2 subscripts to indices, you can track any decision variable you like. Okay, so let's see the results here. Decision variables. As you can see here, it says let xij, I is the start point and j is the finish point. I can be origin node or transshipment node. J could be, can be transshipment node and destination node. The logic is exactly the same as before. So xij denotes the number of units shipped from node I to node j, no matter if it is origin node or transshipment node or destination node. But obviously we know that I never can get a destination point, because when you get I as a destination point, what would be j? Because there is no layer of anything in our model, in our network for that. And also we know that, for example, let me give you this example to avoid make any confusion creating. See, when I say x1 3, you see 1 is a origin and 3 is a transshipment node. But if I say x3 to 5, 3 here is origin in comparison to 5. And here, because we have x14 denotes the number of units shipped from Denver plant to the Louisville warehouse, and so on. Okay, when you are good with the decision variables, now is the time to go for the constraint. Take your time for checking the constraint that you already know about them. I'm not talking about the new constraint. For the transportation problem that we had before, we had some constraints on the supplies. Also, we have some constraints on the demand. Just try to check them with this graph you see in front of you before we proceed to the next slides. As a review exercise, do this activity. Write down the supply and demand constraint according to this graph you see in front of you. Since it is some sort of review session and we have discussed these things before, even you don't see the title of activity for that. So just to catch up, pause the video before I show the answer for this semi-activity. Write down the supply and demand constraint. Okay, let's check the answer for the supply and demand constraint. As you can see, we have here 6 constraints. 2 of them are related to the supply and 4 of them related to demand. And as I mentioned, they are exactly the same as we discussed it before. Why we have only 2 supply points? Because 2 supply constraints, because we have 2 supply points. Why do we have 4 demand constraints? Because we have 4 demand nodes. So according to the things we discussed before, okay, x13 plus x14 must be smaller than the capacity of this plant. The same thing for this one. And here, when we get to this part, for example, for Miami get its input from 3 and 4. So you see x3 6, x4 6, 6 shows Miami, the summation must be equal to 150. Again, we discussed this before, why here it is equal or smaller and here it is just equal. Let's go for another one. Let's do something completely. Why we don't tackle these things? Because they are not demand or supply nodes. And let me give you a trick about how to handle this. When you check, for example, Kansas City, and you don't see any constraint about demand or supply, so it means that you don't have to get it involved in this series of constraints. So here, let's go for New Orleans. New Orleans gets its input from 3, Kansas City. So 3, 8 plus x4, 8. And since it is a demand point, equal to what? Equal to 300. And so you can handle the rest like this. x3848, 3747 for Dallas, and the demand is 350. Okay, take your time, pause the video, try to write down everything that you see here, and after that check it with the answers.